We're now going to go beyond simple models for molecular distributions and talk about what the real result is for an actual set of molecules. Now, the whole idea here is that we want to, one, find the distribution, so the set of values in J that maximizes the microstates. Okay, this is our common theme. Now, when we do this, we want to impose the constraints that we talked about last time, where we're going to have constraint for the number of total number of molecules. So that's the sum over all those distribution numbers has to be equal to the total number of molecules, and the sum over the energies of the states has to add up to the total system energy. Now, as we do this, there's a couple of things I want you to bear in mind for these systems. One, n is going to be huge. I talked about this last time. It's going to be on the order of 10 to the 23rd. So it is a large, large number. All right, we're also going to find, or what we do find, I should say, in the case of molecules, is that we will always have the situation where the degeneracy is much greater than the number of molecules that are occupying a given energy level. Now, it turns out that this is actually necessary given some of the assumptions we made in developing our formula for W, that this particular condition helps make that formula accurate. Okay, I'm not going to belabor that point too much, but I want you to be aware of it. Now, the whole business behind maximizing or optimizing the number of microstates and imposing these pair of constraints involves a special mathematical procedure called the method of Lagrange multipliers. So let me write that for you. Method of Lagrange multipliers. I am not going to provide a tutorial on the method of Lagrange multipliers. It's a beautiful method that allows you to optimize multivariable functions subject to constraints. It's an incredibly powerful method to use, and it's one that's well worth learning if you are in a subject, if you're in engineering or in physical chemistry, where you need to apply mathematics to a variety of different kinds of problems. I'm not going to talk about it so much other than to say that using this method is going to introduce two unspecified parameters, and those parameters are going to be labeled alpha and beta, and we'll actually give the solution for those two parameters as we talk about the solution. Now, it will probably relieve you to know that I'm not going to go through a detailed accounting of how we actually solve this. It's not especially difficult, but it does require a bit more math than I really want to go through in this course. But if you're interested in learning more about it, I'm more than happy to recommend some fairly straightforward textbooks that can describe for you how to apply the method of Lagrange multipliers to find the most probable distribution. However, I'm going to get to the bottom line, and the bottom line is this, that in the most probable distribution, we can write down an expression for the population, the number of molecules in state J, that is given by this. It's given by the degeneracy of that state times e to the minus alpha, where alpha is this Lagrange multiplier parameter, times e to the minus beta, the other parameter, times the energy of that jth level. All right, this looks like a deceptively simple result, but we'll see that in fact it's incredibly powerful. And as we explore this a little bit more, we'll find that in fact it is really an amazing formula, and one that allows us to calculate all kinds of things about different sorts of systems. So now the question is, how do we find these two parameters, alpha and beta? All right, I'm going to show you explicitly how to find alpha, and then I'm going to hope that you'll trust me in terms of what beta is. But if we apply this constraint of the total particles, we would have n is equal to the sum over n sub j, which is g sub j, e to the minus alpha, e to the minus beta, ej. All right, now this part, e to the minus alpha, doesn't depend upon the summation index. So that means that we can take it outside the sum. This is always true. If you've got something in the middle of a sum that doesn't depend on the summation index or doesn't have any dependence on it, you can take it outside the sum. and we're left with these things that are inside the sum. Now, this is going to seem like cheating, but I'm going to define all of these things that are inside the sum as equal to something called little z. All right, I'm just going to say this is equal to little z. Since we're summing over all the possible j values, this thing is a number, basically. This particular z that I've defined here is something we call the partition function. Now, I just said it was a number. Why am I calling it a function? Well, it's actually a function because of this parameter here, and we'll see when we find what that parameter is that it does impart some functionality to this that is going to matter. But if you'll just trust me for now that we have a partition function that we can evaluate, at least in an approximate way, or if not an exact way, then we have this number times this factor here is equal to the number of particles. So in effect, what I can say is, in solving for this e to the minus alpha, I can say that e to the minus alpha is equal to the number of molecules in the system divided by this partition function. All right, well, this is a nice compact thing. What if I now substitute this into the formula that I have for this most probable distribution? All right, so now I have that the population of the jth level is given by the degeneracy of the jth level times n over little z times e to the minus beta ej. All right, well, at this point, I'm going to leave it here, but eventually what we're going to do is we're going to solve for the other parameter beta. But let me point out something. What if I divide both sides of this equation by the number of particles, number of molecules? So in other words, on the left-hand side, I'll have nj divided by the number of molecules is equal to gj times 1 over z times e to the minus beta ej. And let me clean that up a little bit. Let's make it 1 over z in front times g sub j e to the minus beta ej. But what is this thing over here? It's the number of molecules in state j divided by the total number of molecules. So we can think of this as basically being the same as the probability of being in state j. So it's really a probability. Which also tells us that this partition function is a way of normalizing this distribution so that we have a probability out of it. All right, this is a really important interpretation of this, and it's one that's going to help us a lot as we move forward. Now, if I were to similarly use the constraint for energy is equal to the sum over all of these things, n sub j, e sub j, it turns out that I can ultimately show, but I'm not going to go through the details here, I can ultimately show that this average energy of a molecule, and I'll call it the average kinetic energy, is equal to 3 over 2 beta. And I'm starting with this, doing a little bit of mathematical manipulation, I can ultimately get to this result. But we know from the very first class of the semester that this is also equal to 3/2 times the Boltzmann constant times the temperature. So now if I have these two bits equal to each other, that's basically saying that 1 over beta is equal to the Boltzmann constant times temperature, or I can simply write that beta is equal to 1 over kBt. And this result is one that is very central. This means that this thing, e to the minus beta ej, is actually e to the minus ej over kBt. And this thing here is something called the Boltzmann factor, after a famous scientist, of course. All right, this Boltzmann factor now is going to be the thing that really is determining the relative probabilities of different states. The states that have energy Ej are basically given, their probability is given by this Boltzmann factor divided by the sum over all the Boltzmann factors, which is the partition function. All right, so This has been a quick dash into most probable distribution, but in effect the most probable distribution is the one that has nj equal to 1 over the partition function times the degeneracy times e to the minus ej over kbt. And here the functionality that we're worried about with the partition function is shown to be temperature. The partition function is implicitly a function of temperature.